Okay, good evening. I welcome you all for the day 4, session 7 of 6 days online FDP titled Innovations in Additive Manufacturing for Green and Sustainable Future. Here we have expert Dr. A.K. Lakshminarayanan sir with us. I'm, I'm very happy to welcome sir. Welcome you, sir.
Yeah, no, thank you,
Now
thank you.
the session 7 deals with wire arc and friction-based additive manufacturing. I kindly request Dr. A.K. Lakshminarayanan sir to start the session 7.
Oh, still we wait or we can start?
Yes, sir. We can start, sir.
Okay,
They will
right.
join.
Okay, right. So, are you able to see my slide moving?
Yes, sir. It is moving.
Okay, right. Right. Good evening, everyone. So, I am again thankful to the organizers for inviting me to deliver the lecture on wire arc additive manufacturing. Earlier session, we discussed about the basics of 3D printing and various technologies available in 3D printing as per ASTM standard. Now today we will just go through basic, mainly wire arc additive manufacturing and friction based additive manufacturing also. Uh, in between, from my previous lecture and today, I hope you heard something on solid state process also. So I will mostly I will concentrate on wire arc. If anything is missed in the previous lecture, from other uh, speakers, then I will try to cover that those processes. And if you have any doubt on solid state also, I will just try to discuss. Right. So so whatever we are going to see. You can see it from this slide. Basically, if you want to deposit metal through additive manufacturing, your heat source may vary. Your heat source will be different for different. One second, I got a call. So my heat source will be different. So in this case, mostly this in the graph you can see various processes mentioned with respect to the feature size in x-axis and the in y-axis the deposition rate, how much material you can deposit with respect to particular hour, that is given in the y-axis, but it is in the log scale. No need to worry about the actual data. But all these process comes under either directed energy deposition or powder based process. Mostly the raw material whatever we use is powder based or wire based. Both you can use. Both wire and powders you can either spread over a bed and try to melt with laser, what we call it as laser or electron beam, which is given here. You will just in the build platform just spread the powder here. Okay, then melt it through laser or electron beam through some scanning method. Okay, so that is powder fusion bed, which we also discussed in the last session. So that is one. Laser metal deposition is the next thing, which comes under whatever it goes beyond this. Everything comes under directed energy deposition, where you will have a heat source. You will have a heat source. Sorry, some problem. One second. Okay. You will have a heat source. Directly, you will just feed the powder in the arc or laser beam or electron beam. Then just melt it, and the molten droplet will be transferred to the substrate, and you will get the component. So that is laser metal deposition or arc based additive manufacturing, which I will concentrate because basically I'm a welding guy, where I use a lot of welding processes. So arc based welding process is very popular. uh, One thing you have to understand is, if you go this direction, arc based additive manufacturing, you can go get higher deposition rates, whereas the feature size, suppose the surface roughness, or in other terms what you can call it as surface roughness, is very high in case of arc based additive manufacturing. When you go lower than, when you go towards powder fusion bed, where the surface roughness is somewhat less, no, it's a surface finish is somewhat good, roughness is less. Okay, so this graph we can identify two things. We can understand, one, what are the different processes by which you can deposit material. Mostly two methods. One is powder fusion bed, where powders are spread over the surface. Just melt the powders with a heat source, laser or electron beam. uh, Other aspect is directed energy deposition, where powders or wires are being fed into the arc column or laser beam or electron beam. So it will be melted and it will be deposited. Your melted particle will be transferred to your substrate, and you will get the component. No, your torch will move according to the program, or if you already have a sliced model, if you have the G code, then it will move accordingly. So this is a component made through powder metallurgy. Last session I told, mostly in the literature, 10 to 15 microns. Powders are spherical nature. The morphology will be spherical, which you can see from the image is here. Scanning electron microscopy, captured through scanning electron microscopy. So that is one thing which you can understand, and you can see these components. This is a monoblock, and whereas this one is built with some supporting member. These supporting, like what I shared, when I shared about polymers, where we can generate support when it is overhanging. This also you have to remember, 45 degree, up to 45 degree we don't want any support member. Anything greater than 45 degree, of course, we need to have 45 to 90 in between. If your angle is there, then of course you need to provide a supporting member. So this need to be removed after the complete product is manufactured. So through post processing, always whatever product we make, we need to do some post processing, either heat treatment to get the homogeneous microstructure, homogeneous property, or some kind of finishing operations. Sometimes it is required. So especially when you have support members mentioned, just given in the picture. So when you need to go for metal additive manufacturing, suppose if you want to develop products, prototypes, models, that if that is a case, you can go for additive manufacturing. And if you want to produce low volume components for pilot production, then you can just go for additive manufacturing. In metal forming operation, as I mentioned earlier in my session, if you want to do fabricate some dies, if your dimensions are keep on changing because of the production is low volume nature, or batch production, then the tooling cost, manufacturing of tooling cost will be very very high. So in that case, you can use additive manufacturing to fabricate the dies. Then you can bring down the cost of the total process. So that is one reason why we choose additive manufacturing, metal additive manufacturing. Then if you have a complex geometry, there also you can use additive manufacturing, because when you want to prepare a blade, turbine blade, so it looks, the profile will look like this. One side it is 3 mm, other side is 1.5 mm. And also it will go, when you, it is not a straight profile. So when you go up, usually there will be some angle when you construct a turbine blade. There are several reasons for heat transfer reasons, thermal reasons. So if you want to build that kind of complex geometry, then additive manufacturing is one of the versatile process where you can just build those complex parts. Okay. So regarding material, you can have aluminum, cobalt-based material, tool steels, nickel, titanium, stainless steel, or any other precious metals, copper and others like titanium and some material. They are, as I mentioned in the last session, they are highly reactive. You need to give protection, that is essential. Some times, no, titanium and magnesium, as I mentioned in the last session, they are belonging to HCP structure. Whenever you see this structure, the ductility is very low. This also I shared. Whenever you see some material with HCP structure, the ductility of those materials are very less. If that is the case, deformation based processes are difficult to fabricate these material components made of this material. So then you can just think of additive manufacturing. You just This is the powder based fusion. Last session I shared. You can just these are the methods. One is powder based. Binder jet is also one of the process. We are going to concentrate this one, directed energy deposition. Here the very important aspect of the metal additive manufacturing here is, you can see two components in the photograph. One is outer surface is high density, hi- high dense, whereas inner surface is of low density. So that such a structure you can create using additive manufacturing, which is very very difficult if you want to fabricate these components through conventional method. So if you see here, the inner surface is of high density, the outer surface of no porous structure. So the same thing if you want to produce in conventional route, it is not so easy. So that is one thing you have to remember. Same thing, there is another slide, the same thing. So here if you see, outer side is of high density, inner is low density, whereas here the inner side is of no sorry high density, the outer surface is of low density, right? So such a components, no, that is why no, everywhere we cannot use additive manufacturing. It no, you need to analyze and know what are the problems which are there in conventional route, where you can supplement additive manufacturing. So additive manufacturing, we can use it for specific applications. This is one of the application where gear hubs, where the internal holes, you just check this shape and size of this internal hole, which is very very difficult to make in conventional process. If you want to make this hub, gear hub, so it's very difficult. No, such a features you can generate in the component. That is also another advantage of no metal additive manufacturing. This is one of the application where aerospace fuel nozzle, you just these components, either you can fabricate as a single mono block, or even you can just make it as a joint once you develop different parts and try to join. This is one of the hydraulic crossing block, where you can just imagine the features generated in the component. You can just see there is a hole with partitions in between. So such a features, no, it is not so difficult to fabricate using convention using additive manufacturing, especially powder based are very suitable for this to fabricate such a component. uh, Basically additive manufacturing, metal additive manufacturing I'm talking about, no, even some are plastics, but there are several methods by which you can just manufacture. Here two classification which is related to today's topic. Maybe you might have seen solid state additive manufacturing through other speakers. I will go through that if time permits. I will go through that. Otherwise, I will just restrict myself in wire. I will share some of the interesting concepts. Maybe you might have seen. You just at the end we'll discuss. So fusion-based additive manufacturing we are going to see. Mostly we will concentrate on wire arc additive manufacturing. Solid state. Most of the welding process mentioned here is friction-based. Uh, so two very important process may be covered by other speaker. If not, I will cover friction additive manufacturing. There is very interesting topic is additive friction step. These two are very interesting topic. For friction stir additive, it will not take very good machines. If you even if you have a milling machine, you can just do this work. But additive friction stir, or there is a company called Meld, who are very popular in this process. Though this process was established by Aeros Probe, there is a company Meld which is now widely used this process for different application. Maybe I will show that slide. You'll understand. I will show some videos. Okay, based on these processes, whatever I just encircled, they are all solid state process where the material is not subjected to melting. We will see what are the advantage of those after seeing. This is one video where it will demonstrate the directed energy deposition. Here the wire is melted with the use of laser beam, so the continuous bead will be deposited. Only thing is the path through which this should go is decided by the G code, which we can generate either by CNC, or if you have a robotic control system, just you can just use this process. So you can see the laser beam is coming out. There is a wire feeder, so through which the wire is fed just to the beam, and you can just deposit. This is one of the fastest technique, but since the laser beam size, no, it is very less, the bead of the deposit, that also it is restricted. That is, this is somewhat low volume deposition when you compare with the wire arc additive manufacturing, but plenty of application already people have done using this process. Just we one sec. Here the advantage is, no, it's not like powder where powder is wasted. Some amount of powder is wasted in the. This is from the piston top. They are depositing similar kind of application. Even wear resistance application they do use to deposit. Laser based additive manufacturing just deposit certain layer over the piston, which is being done for improve the thermal efficiency of the cylinder engines. Okay, I'll just take this video, one more video, how you just see the various components that can be fabricated using this. Just to have some idea how it works. Now, any complex shapes can be built by this continuous layering. You just see how it works. Now, this is the close-up shot. The It is captured how the liquid metal is transferred. Yeah, see, non-plane, not in a single plane. It is going into different planes. You can just deposit based on that. For that, you need to have some weld positioners so that the movement can be achieved. Yeah, this is after machining. You just just see the inner surface and the outer surface. After machining, it will look like the one which. This is one more video. How you need to have some positioner, welding positioner, in addition to the robot head or CNC, such a way that you can build these components. Just imagine this build. Once again, I will play that. The same thing if you want to build. I just stopped the video. Just imagine this is a very thin section, and the cross section is also continuously varying. So if you want to build the same one through different conventional route of manufacturing. Either you have to just take a sheet, roll form it, try to weld and do the finishing. That is one method you can build it. But there is always a weak link, what is called weld bead line. So always when you subject it to loading, the weld bead, the failure may takes place in welds. So that is this is a single mono block. That is advantage of this process. I will just play this one where you the profile, you just check the profile. I want to show different videos so that you will understand what are the profiles you can do. But if you want to develop such a system, you need to work for years. These machines are very costly. So but our own machines we can develop, but you have to understand the process very clearly. uh, so this is one video. Not only no deposit complete product. In addition to that, if you want to modify the some features, if you want to create, somebody is so mute. No, whoever is just mute him. Because I am coming out and mute, just doing mute. Please, whenever there is some noise, please try to uh, mute the organizer. I request the organizers because it will disturb the presentation. Okay, so you need not to do want to build a complete component. If you want to add features to the existing component, you can do that. This you can see it from this video. You just see here all these features are being created by additional deposit. Again, you need to do programming. There are a lot of skills you need in programming, and just fixturing everything. This is a 7-axis system where different axes are being used to deposit at desired location of the component, not on exactly complete component. So desired location, if you want to modify, you can still modify that. Maybe I will put a few more videos. Just this is one video where hybrid techniques, say for example, it is being deposited, then they are doing simultaneously doing the machining. You can see this is a deposition. Now they are doing the machining. Just use some milling cutter, try to do some material removal in the inner surface. uh, I will show this video so that you will understand. This is very popular nowadays. Do the uh, deposition. You see, you just imagine. I'll just play it again. Maybe lot of spattered particles are the outer surface. Those are being removed. See, I request again. I am requesting the organizers to just take care of this. Right, always the noise is coming. It is very difficult to conduct the session if it continues. Please, please mute the participants when, as and when, no, because I am coming out and just doing the mute. Uh, right, okay. So I will just play this video again. I will just stop wherever it is required. Yeah, you just see the surface. All are the particle which is coming out when you deposit the spatter which is coming out just to on these onto the surface of the component. For that you need final machining. This comes under post processing, but there are machines addition, not remove the component from the machine and just fixing it onto the lathe, then removing the material. That is not the case. So instead, directly, no, simultaneously you can do that. What we call it as hybrid manufacturing, hybrid additive subtractive manufacturing. That is also very popular nowadays. So this is one application where if you want to deposit a thick layer of cladding over the another material. I'll just play this video. So this just they will deposit. Maybe you will get a better view once on the top surface is shown. Yeah, this is, there's sometimes, if you have a mild steel, if the corrosion resistance is poor, then you can deposit a thick layer of stainless steel. Also, there is a concept of, the concept called functionally graded materials, where you can just deposit different composition in each of the layers. Say for example, we have started some work where we used to deposit radially functionally graded material, where suppose you just check this video, where the first layer, we used to twin wire system, where one side is one wire, other side is another wire. We will vary the composition 20, 80, 40, 60, 60, 40, 80, 20, and finally 100%. One side, if you see one material, other side you will have another material. In between, there is a gradual transition. So what we call it as functionally graded material. There are several applications for that. Maybe right. So this is regarding directed energy deposition using laser. Okay, laser based additive manufacturing. Okay, so now we will just move on to wire arc additive manufacturing. Again, I'll just take the pointer 1 second. Again, this comes under directed energy deposition, where here the feedstock is metal wire. We will be using a wire, and the speed rate of the wire can be controlled. You can just control, and the it is fed into the it will be just fed into the arc column. Okay, where you place the wire, that plays a crucial role. You can place the wire here, or just here, or into the core position from the substrate. This is also very important, where you are keeping the wire, whether into the core, or just no on the outer surface of the arc, or just near the torch tip. Where you are keeping the wire plays a vital role. Especially we did a lot of studies on that. uh, we'll see that one by one. We will see that basically this involves the motion, whatever you witnessed, you may achieve through robotic system or CNC system. Okay, here first thing is you need to prepare substrate. So any deposition, if you want to make, not like uh, polymer printers, where you will have a heated bed, your material will not stick. Once it will stick initially until it builds, then you can easily remove it. But it is not the case in metal additive manufacturing, especially when you are working on directed energy deposition, where always you need to have a substrate. Suppose I want to print stainless steel. Uh, Wire I am using stainless steel wire, maybe 316 or 304. Uh, I will select the base material, which will also related to austenitic stainless steel. When I deposit 409 or 430, this is a ferritic stainless steel. I will select a ferritic stainless steel grade uh, stainless steel, so that the first layer itself, the dilution, if even if there is a dilution, there will not be any issue because of the same material. If you use different material, there will be dilution. Dilution is nothing but when you deposit the first layer, how much your base material will get mixed into this in the first beat. So it will naturally alter the property. If this and this are two different materials, it will alter the property of the first layer. Maybe you will deposit as you go higher wall heights, then you can you will remove it at the end. But you have to select proper substrate. That is very important. Then wire deposition, warm deposition is nothing but first you have to generate the tool path. Either you can write your own G code, okay, for motion, or you can use slicing software. But if you use three-dimensional part, and if you have sliced component, currently the machine is very costly. But for our research, because most of us are we are doing research, so we can build a wall, cylinder, or simple geometry, then you can work on it. So it involves rolling also. I will show one of the process where after every pass they will use a roller to compress it for particular purpose. I will explain that. Then once deposition is over, you may need heat treatment. Why we want heat treatment? Suppose if I build a wall of this size, the property may be different with respect to the orientation, because Initially you have substrate here, all this area is exposed to air, okay, surrounding, right? So your heat will transfer always quick faster than here. It will be through conduction. Here everything, it is radiation, so there is always a thermal gradient between this layer and this. So there is a difference in the cooling rate from here to here. Naturally, no your microstructure will be different. Either the phases present in that is different, the composition of the no material there is different, or the size of the grains, it will be differing at each of the location. In order to make it homogeneous, you may need no forced build treatment. Again, depends on what type of material you are going to deposit. Say for example, I am depositing a titanium aluminide, then there may be aluminum content is higher here. If it goes lower here, maybe you have a titanium substrate. So because I am using two wires no now, so here this is a titanium plate. So titanium is higher here. As you go up, your aluminum content may be higher because of the density difference. Okay, so we'll see that because we are doing a lot of work with a government sponsored project. I will show that. So very important thing, we have to understand why we need heat treatment here. Heat treatment is to bring the material homogeneous everywhere, either of microstructural difference or property difference. All those things are there. You need heat treatment. Once heat treatment is over, then you may need additional machining, because all these process, whatever, either you use laser based or wire arc, your surface roughness, it looks, when we draw like this, it is very straight, but when you see closer to that, always your surface looks like this. Maybe it will vary, for example, in laser based, it is 200 microns. In wire arc, it may be go up to 2000 microns. Okay, that may be different for a different thing. uh, so you need to do machining. Finally, you need to remove substrate, because whatever you build here, it will be, you need a base member. So suppose I build a wall, no I build a wall, so I need to remove this. So that is the substrate removal, either but by electrical discharge machining, or even abrasive water jet machining. Through that you can remove the substrate, or simply sometimes if the material is so easy to machine, then you can just use lathe to just use parting of tool and then remove it. Finally, you need to do inspection. Either inspection is, there are non-destructive testing method, destructive methods. No, that you have to do for a, when you go at a component level, you have to do non destructive testing methods. When you are at prototypes, cut up evaluation models, then you have to do destructive testing methods to do that. These are the steps involved in wire arc additive manufacturing. Why we want to go for wire arc when you have laser, electron beam, those are no there. Yes, the arc power used no is to deposit. With respect to the deposition rate, it is 1/10 of the laser and 130 of no electron beam generator. That will cause is highly economical with respect to the deposition rate. Okay, so deposition rates in laser or electron beam is very, very less. Whereas if you go for wire arc additive manufacturing, for example, if you use GTAW process, gas tungsten arc welding process, many of you, I hope you are all from mechanical engineering background. So if not, even if from physics, you not worry, I will just explain the process. uh, when you have GTAW, you can just deposit 2 kg per hour. So suppose when you use GMW, you can use 6 kg per hour. So this is possible in wire arc additive manufacturing. That is why the arc power is being preferred over laser. So you cannot avoid laser and electron beam. Still, for crucial application, this is being used. But for large volume deposition, arc power is very useful, considering these facts. Okay, especially the deposition rates. There are other advantage, especially there are problems with laser-based additive manufacturing, especially when you want to deposit component or when you don't fabricate components. Aluminum, copper, magnesium, they are highly reflective. In if you want to use laser-based, laser melting, your metal need to absorb the laser. So since aluminum and copper, magnesium, they are highly reflective, the surface, uh, it is not a good choice. Laser is not a good choice. The absorption is less. The energy already, as I told, the energy is very less. Only 20% or 30% of the energy is being laser energy will be used to uh, melt the material. All other will be either radiation or heat loss, because of the not absorbing. That is a problem. Electron beam is also one of the very good process for highly reactive material, but you need vacuum. Though no, there are even in electron beam welding you have low vacuum, medium vacuum, and high vacuum. Even non-vacuum non-vacuum electron beam processes are there, but that is not good for additive manufacturing. So definitely you need vacuum space, uh, which uh, which causes no operation difficult, because you cannot see through no completely, you cannot visualize the product while deposition. You may need cameras and other thing to see that, and product size is limited because you need to construct a vacuum chamber. So that is the thing. Okay. So if you our process selection is basically based on these requirements. When you want relatively higher deposition rate, like when you want to go to 6 kg per hour to even 12 kg per hour, so this will be the process. Low heat input, again, it is debatable when you compare with the laser and electron beam, but you can have some process like plasma arc, where heat input is being reduced. That is the thing which can stable process. This also you can create stable process. The processes basically these three. Still there are variations within that. Gas metal arc welding, either MIG or MAG, inert gas or active gas. Either you can use argon or CO2. You can also use direct current or AC current, but because whenever you deposit material like aluminum, there is always a problem of alumina on the top. So if that is the case, to self clean that, you always need to go for AC current. Okay. So there are certain process developed by this company Franius CMT, where the wire, instead of feeding the wire continuously, in every step they will feed that, they will create the short circuit, melt the wire, they will retract. During the transfer they will retract because it will reduce the heat supply to the molten pool. So this is very popular in additive manufacturing. Even you can have multi-wire GMW, where two wires in tandem they will use. Both the arc will be created in this and this, and it will deposit. This is one process, very common process used for additive manufacturing. There is another process, TIG, or no, this we can call it as GMAW. This you can call it as GTAW. Okay. So these two process we are working on different materials. We have systems for depositing different materials, almost starting from aluminum to titanium, titanium aluminide, nickel aluminide. We are doing a lot of work using these process, and this also we are using it for single material. Maybe I will share some of the slides which I have, which we have done in our center. So basically, you have for wire arc additive manufacturing, you have gas tungsten arc welding, gas metal arc welding, cold metal transfer. Again, it's the same of GMW, except there is a wire retraction. Okay, so you can see here, this is a GMW process. Maybe those who are not aware of this, I will just refresh and I will go faster. There will be wire feeder. The wire is fed. There is a workpiece. just the arc is created between these two, and the wire will be melted and it will be deposited. This is a very faster process. You can see here in the video. You can build once you know the proper path. So just you can deposit like the one which you see here. So this is the wire is along with the welded torch, this coaxial with each other, and it is easy to generate path. And even programming through robot is also easy. Most of the systems where robot is being used is always attached with a GMW machine or even CMT. But our robot, we attached gas junction arc welding for the purpose of twin wire, which was sponsored by no DRDO. I will show that. Okay. So one second. This is GTAW. Uh, it's not like the earlier one which we discussed. Here we will be using a non-consumable tungsten electrode which will not melt. But here the wire is fed externally. You can feed single wire, twin wire, even more than one, three wires also we are planning to develop ternary alloying. That also we can do that. Only thing is the concept you have to understand GTAW and GMW. GTAW is the process where there is a non-consumable electrode which this will not melt, whereas we will feed the wire externally. Uh, the power supply and all, you need not to worry about it. Only thing you have to understand this. Okay, maybe I will just. This process is very quiet process where it's not like the GMW process. I'll just play this video. There is a tip you can see here. Maybe I will pick laser pointer. This is the tungsten tip. The arc, you are able to see the bell shaped arc. The wire feeder is from this side. You can see just melting. No, you can feed the wire no any directions, but again you need to do a lot of studies on that. We did no extensive study on where we need to feed, especially when you use two wires. Uh, you need to have proper mixing of that. Maybe I will show a few more videos so that you can understand. The wire is fed externally here. You just watch this video. You can see the bottom layer is there is one bottom layer. You are depositing the second layer. Here you can see the wire is coming inside, just go into the arc column. It is being deposited. This is how actually this is a close-up view. If you have a camera which you can, when you capture this, you can do a beautiful work how your metal is being transferred, that you can capture from different views, and how it is contributing to the microstructure and all those aspects you can relate. Recently, I visited exhibition there. No, these cameras, no more for capturing this without the by masking the arc. It is around 5 lakhs. But you have, when you want to capture, the temperature of each layer, then if you have 15 lakhs, you can buy a camera. That is also there. So if you see this component, you can understand the size of the product, which somebody asked in the last session. I'll just play this. You just watch this how big this component. Imagine the size of the component. It is being built by wire arc additive manufacturing. So only thing is you need to the path generation is one of the complex process. So such a big systems, right? Very big systems, big components you can just build using this. And this video maybe it will show different how it is being deposited, what is the shape, different shapes. Now bottom you will have one direction. It is like a skewed geometry. I told you, you see, just see the shape and size. It's not the planes are not same. You'll have different planes. That is also possible through wire arc, right? Maybe this one. This is a nickel aluminum bronze, especially for ship propeller. They fabricated this by continuous deposition. Maybe in between they have given some Maybe I will play it again. So 3 days they took and they deposited that, and finally they did finishing. We also did some work. It's not a direct deposition of propeller, but we are doing it for some studies. Nickel, aluminum, bronze. After no deposition, they will do inspection, which is called post processing. Then they will put it into application. Okay, you can Netherlands, they had done that, and they successfully used this in the shipyards. So this is the basic setup. No, it's like similar to welding. Only thing is, no, you have to set, arrange system such a way that you will see how to progress. Okay, this is a work table. See, two things you can do. Either you can move your workpiece, or you can move your torch. Okay, based on the requirement. Okay, or based on the size of your machine, both is possible. Okay, both are possible. So here you have a argon cylinder. It is going to the weld torch through which it is coming out. Additional connections are being taken for shielding, because once you deposit here, suppose if I'm depositing here, these areas are still in hard conditions. So maybe at higher temperatures. So this should be protected. This should be protected. So for that, they are using shielding gas, additional shielding gas. Either you can use a single system, or even additional multiple systems also there. Uh, Again, there is another system which is attached to that. Different purpose. Okay, maybe some active and some noble gas they use for different materials. Maybe mild steel, usually mild steel, argon plus CO2 they use 80-20%. It depends on what material you are doing. So this is the basic setup. There is one more process which is very commonly used nowadays, is called plasma arc welding for additive manufacturing. This process is very much similar to GTAW process, except the design of the torch. Only thing is, you have two covers and your tip is inside. In case of GTAW, your tip will be protruded outside. Because of that, your arc will get diverged, because there is no restriction from this side. The area exposed, the your substrate area exposed is large because of this divergence. But as whereas in this case, it is kept inside. It is kept inside because of the this restricts the arc. Also your argon is coming out, no, it will give restriction. So your beam, when you see in plasma, so it will look like this. So in case of GTAW, it look like this. So I hope you are able to understand that this is diverging arc. This is almost parallel beam. So because of that, your depth is less here. It is wider bead deposition, whereas in this case, it is a very narrow and it is longer or deeper penetration you can go. Or in other ways, in additive manufacturing, this is the case in welding. Just to understand the basic difference between those who are not aware of this process, I just sharing this. They are available in books. Just somebody from physics or somebody is there just to understand. So in plasma, the beam is parallel. The area exposed is very less. So heating and cooling rate are faster, and the supplied heat is also less. The what we call the specific heat energy, but is through kilojoules per mm square. If you calculate, since mm square is less here, naturally, no, is very less heat supply to the. So your total setup, you need to have a welding machine. You need to have a robotic controller to control that. You can either using computer if you have a software, or you can have a teach content through which you can do programming. That is one thing. So you need to wire feeder, you need to additional, because if this is not GTAW, GMAW, you need to additionally feed that welding machine. Any machine, no, there are basically you can have, as I mentioned earlier, you can have robotic or CNC. It depends on the cost. Basically, robotic system are cheaper when you want to build bigger CNC system because of control systems. If you want to have Fanuc or any systems, so they are very costly. Sometimes you can also have GMW process and GTW process combined both to increase, as I mentioned, because this is 2 kg per hour, this is 6 kg per hour. If you want to deposit more, and you can want to mix both of the process, still it is possible. People have tried this. uh, they have deposited material. So this is one of the process called cold metal transfer, which I showed. Just maybe I will you just see short circuiting, they will retract, then they will deposit. Yeah, I will just stop. Yeah, I'll just play this video so that you will understand how it really works. You can just closely observe the wire. It is going and just touching the surface and getting short circuited. Thereby, the molten droplet is formed. Once it is formed, no, they will just retract it. So because of that, the heat supplied to the material, right, that is reduced. So thing is, wait a minute, I will just take this pointer. So you have now the wire, when once it touches, there is a droplet available. So the current is still passing through this. There is a droplet available. But once we need to transfer this, once there is a liquid, liquid is formed. So while transferring liquid metal to the workpiece, I don't want to have the same heat there. So I can just reduce the heat just to by retracting. This is one method. There are other methods even in GTAW process or the GMW. There is a process called pulsed welding, where instead of keeping constant current, what we can do is you can just do pulsing. So this is for melting, and this is for when during metal transfer. So thereby, no, your heat supplied is very less. Okay, that is what is given here. Less distortion, almost zero spatter, because GMW is known for spatter, but the deposition rate is slightly reduced because of this. It is not as much as what you can achieve through GMW. But when you consider the spatter, the particle which is coming out, uh, this is good. Okay, secondary processing. This video will help us to understand the capability of how we can build system to fabricate components. You can such a overhanging features is also possible. Maybe you just watch this video in a very uh, yeah, real time. This is real time. Just they will touch and go, drop it up. They will attach such a overhang because it will take some time for solidification. So there is no support system required for this. Now, if you provide support system of the same material without not reducing the density, it is very difficult to process again. The reprocessing is always a problem. So always there is a trade-off between the deposition rate and accuracy and surface finish. This we have to concentrate. Large parts always need high deposition rate, but you can have tolerance for dimensional inaccuracy. That is one thing you need to consider. Small parts, you always have best accuracy with the expense of productivity. But please remember which application you are going to use, especially when your material, when your component is subjected to fatigue. Always fatigue starts from the surface. If your surface is having no is having this kind of undulations, this will cracks will induce this as crack point or initiation point, and it will crack will no, initiate and propagate, and finally it will fail. So surface finish is essential where fatigue is in consideration. That is the thing which you understand from the graph. Uh, this is also very important way what approach you are going to deposit. Either you are going in the same direction, opposite direction, because when you build a wall, so from here to here, if you deposit, where you most of the time when you don't have robot and when you don't have touch sensor and seam tracking, there are two features you want to have in robot. One is touch sensor. To understand, once you deposit a layer, you need to understand where the layer top is there. Then only from there you can, from there, no, the robot can take that as reference, then accordingly it will deposit the next layer. So for that you need to have touch sensor and seam tracking, where exactly it is going. Either it is going at the center of the earlier bead which we deposited, or it is just offsetting from the earlier bead. That again, we need to have these two features. If you don't have that, then slightly it is difficult to control. We have alternate options, very simple approaches are there, but only thing is either no single bead. If you suppose, this is very important actually. Suppose if I wait a minute, my pointer I will take. So suppose I will deposit a single bead. Usually this bead, you may go up to 10 mm. Okay, 10 mm width is possible in a single pass. And if height, you can see, I am talking about GMW or GTW, where you can go 4 to 5 mm per pass. But if I want 20 mm width, what I have to do, I need to go for multi bead. So one bead here, another bead here. Okay, so another bead. If depending upon the width I want. So this is no multi track single bead. Like that, I will build. I will build like this. Finally, I will build a component. Here the important thing we need to note down is, suppose when you deposit like this, there is always a reheated zone. This zone is subjected to reheating. Initial deposit, this is already having microstages similar to this side, but when you heat it again and solidify, this zone is there always. But it is not like, in welding we will ask heat affected zone, but this is a reheated zone. It's not a heat affected zone, it's a reheated zone. Always in when you build structures, the heat reheating zone is always there. For that you need to control strategies. Either suppose one bead, if I deposit like in the way, whether I have to pull my torch extra, no, just retract my torch and go back and start from here, first pass, second pass, third pass, like that, whether I want to do, or just I went to here straight away, I will just start depositing from here itself. So this way you can do. That is the difference from, that way you can just deposit. But again, you have to understand, whenever you do multi pass, multi bead, you need to give certain interpass temperature. Interpass temperature is nothing but the temperature between these two passes. Maybe this zone is expected to melting point and it is getting solidified. When you want to start the next process, what is the minimum temperature I have to keep in the first bead? Okay, this will hold good for any number of beads. Okay, so interpass temperature is a crucial thing which you need to understand. Now, these are some of these tracks, like, as I mentioned, whether you want to go suppose sorry whether you want to go longitudinally, or suppose I want to go transverse, like this, you can play with that. Try to understand how the microstructure varies, how the features varies, everything, no, you can just check. Okay, so regarding material, aluminum alloy, no, almost most of the aluminum alloy here, both non-heatable, heat-treatable alloys are there. Say for example, 5000 series, 4000 series, they are all non-heat-treatable alloy, whereas these alloys 2219, 204, 2319, they are all heat-treatable alloys, which responds to heat treatment. Both can be deposited by either GTAW, GMAW. All these process people have done. This is a consulted list taken from the literature. People have done that. Titanium, you can see titanium 6AL 4V grade 5. Again, plasma GTAW. This is alloy again deposited by GTAW. Steel, if you take stainless steel, or this is a mild steel. This one is mild steel. This is also mild steel. Stainless steels of different grades like 304, 308, 316. This is ferritic Martin 6 stainless steel, 2 chrome 13. Copper coated steel, again, it's a mild steel. You can just refer this. No, these are available in literature. Just refer this. If you take nickel based alloy, is also high temperature application. We did some work on nickel Inconel 625 cylinders we fabricated using GMW process. Uh, if you see magnesium, lot of potential or chance for doing research, but only drawback, what is unfortunate, is the wires. The magnesium wires we are not getting. Some people, I know some people are doing that in our country. They are doing some work, but they imported wires from the China. So if you are able to get wires, then this is a very good opportunity to do some work on magnesium for different application, especially biomedical application, or even for other applications, no, for structural applications, different magnesium components you can fabricate. Because, but it is very challenging fusion based process for magnesium, but still you can do that with some modifications. Hardware system, just to understand GTAW, as I mentioned, you can go up to 2 kg per hour. You can use a CNC robot for all these case. GMW CNC is better. That's why they demonstrate that. All other, just you can go through that. Even tandem, I mentioned 12 kg per hour you can go, but you need to have two wires to deposit such a high deposition rate. Okay, that is, the robot also is very useful for such a system. That is very important thing. So what are the common defects you need to handle it? That is, one thing is residual stress and distortion. Uh, how it is, deformed. Porosity is one of the problem, where if you use a sufficient shielding gas, you can avoid that. Cracks and delamination is one of the problem in wire arc additive, especially as I mentioned, when you deposit one layer, other layer, if you deposit continuously, there may be a chance of crack because of the thermal gradient from here to here. So naturally, you need to, in between, you need to have certain interpass temperature. You have to allow the material to cool down to certain temperature, then you have to deposit. That you have to remember. Otherwise, the delamination most of the time happens here, or sometimes cracks are formed within the component itself. Okay, that is very very important. Especially the cracks are formed when you are using two different materials. Like, suppose I use copper here, then stainless steel here. There is these two are no exotic combination. If I use stainless steel and titanium, it is very very difficult to join. Similarly, magnesium and aluminum. Say magnesium and aluminum, if you take, it is only, this is the 650, this is 660. Okay, so naturally, uh, the melting point is very much similar, but unfortunately, the crystal structure, this is FCC, this is HCP, and solubility level within each other, that is also not good. So, the because of that, those combination, always, whenever you consider two different materials, you need to check the feasibility. You have a lot of scope for research also. So, considering this author has beautifully constructed this radar plot of different material and different defects. So, just for reference, I am just shared here. Titanium, if you consider, except oxidation, everything is good or very low, right? Aluminum, if you see, there is a problem of porosity is bigger there, because you see 5 points rating, that is bigger. If you see any bimetal, deformation is the issue. Okay, so if you use steel, the surface finish is always a problem. Like that, you can just refer. Okay, just refer. Bimetal deformation is higher. Cracks. There is a problem of cracks. Okay, this you can just refer. The scale is given like this: one is slight and five is severe. From that you can just try to understand. Now people have done this comparison. Uh, if you see the um, hierarchy additive management, just to classify based on the hardware, physical processes, which I already covered. Many of that current, voltage, welding speed, wire speed, everything is plays a vital role. These five are very important. Most of the machines, they are in synergic mode. Either you GTW, you have to use constant current, whereas in case of GMW, you have to use constant voltage. So either one of the parameter you need to control. Welding speed is the one. Okay, then wire feed rate, substrate temperature, inter-layer temperature. These are very, very important. All other parameters are secondary parameters. Monitoring, you can do optical. These many of them we are doing that in our lab. Electrical signals we are monitoring, thermal camera we are using, acoustic detection, sound signals. From that, we are just capturing no residual sets, porosity, all these. Okay, application I will just quickly go through because of the time limitation and the. Okay, this one I want to show you. This is the once the one bead is deposited, they will use certain features. The lower rollers they use to just compress the bead. Two advantage. One is instead of this, you will get after compression, you will look like some flat bead, so that it is easy to deposit another layer. After that, you will just compress. This is geometrical feature. You can just see the roller is coming. The other is no compressive residual stress, induce compressive residual stress. Always, whenever you do welding, melt and solidification, there is always tensile residuals. Tensile residuals is not desirable. So naturally, this process will help. This is one of the hybrid process. People have tried, this is actually the real innovation people have done in their work. Okay, this is one thing I just want to show that. So this university, if you can visit those university, Crankfield University, you can see lot of parts, the wing spare, the landing gear, and also the Norsk titanium company, they fabricated this wire arc additive management. These are I forgot to put the scale. You can just, there is one scale which is not very clear. These are very big parts. Okay, the BAE systems, you can see a very large component. You just see this geometry here. It is not same, right? Here it is different. Here it is same. Angles are different. All these are possible there. You can just imagine this component. One side the shape is different. Other side is different. Being hollow inside. Further machining it is not possible, but still they are able to do that using wire arc additive manufacturing. If you see, this is a truncated cone, hollow structure is possible. Mild steel they have done. Uh, this I'll just play this video quickly. Maybe I will not find time to cover wire arc. Maybe sorry, solid state. I will just give brief introduction. I will close that. Yeah, this same thing. I will just skip this. uh, we will come to our lab. This is one setup I have in my lab to fabricate cylinder. This is one of the cylinder which we fabricated using duplex stainless steel. After machining, you can see a very nice material. You can just watch how it works, how much spatter is coming out. This is a real-time video, which we have taken in our lab. Uh, in our center, the facility is there. Where you can deposit any material uh, uh, using this machine. Yeah. So after that, I hope the organizer of this event, Mr. Dr. Rajsekaran, did a lot of work when he was doing his PhD on welding. The same setup we are using now for additive manufacturing samples. Okay, just boiling setup. Room temperature is also for some soft material. This is one more work which we have done. Another scholar who deposited no nickel aluminum bronze, and we are testing different properties, same not as tensile or conventional property. This is another setup we have, tin wire setup, where you can see the robot. Might be I will just take a things. This is a machine, Miller Dynasty machine, capable of doing a lot of parameters you can control using that, especially no pulsing, many parameters you can control. This is a teach pattern through which you can control the robot, and this is the robotic controller. You can see two wire feeders here, one and here one, and different two wire feeders were fed into system, where this is just see, we are just focusing on thermal imaging. Acoustic signals are being recorded. No extensive work we are doing, which we cannot, single lecture we cannot provide everything, but still they are ongoing work. I'll just play this robot how it works, especially twin wire system where you can feed two wires in our lab. So close up shot, I just show this video. Two wires are being fed. This is a different system. Yeah. So you can see just closer view. This we captured in our lab. You can see one side there is one wire is coming this side, other wire is coming this side, and the bead is being deposited. This we have we are doing a lot of different materials we are now trying. You can just see how the robot torch is going up now. It will come and the arc will initiate, and then it will record the temperature automatically, so that heating and cooling rates you can measure, and accordingly no you can uh, uh, so correlate the temperature history with the properties, right? The problem with the fusion, so far we covered fusion based metal additive manufacturing, especially wire arc and laser based also. But the problem is always whenever you do melt, whenever you just bring the material to liquid state, always it will pick up unwanted elements from the atmosphere. And also there are a lot of problems and defects associated with solidification issues. Because of that, people started working on solid state. I hope my fellow, he was in my lab, Mr. Dr. Daniel. I hope he presented that probably, or otherwise I can share. No, this you can just search it. Lot of friction based process. I will cover one or two quickly. Maybe he covered. I hope he covered. These are all our work we have done. No, see, almost I spent half of my 16 years in friction stir welding, where I did PhD. I guided PhD in the same process. Now additive manufacturing, just this comes under sheet lamination. This we already discussed during last session. Sheet lamination. So take a sheet, try to build no product. Maybe I will just quickly show this video. You just see, take a sheets, try to build same thing. If you want to deposit with a wire or powder, just imagine how much time you have to spend. Instead, if you have a geometry of this, take no sheet and arrange sheets, try to build no layer by layer. Finally do some machining with a hybrid machining technique. Directly you get a component. This is the advantage of friction stir additive manufacturing, which we do no for magnesium and for different studies, not for conventional tensile or micros analysis. For different thing we are doing that. For the want of time, no, there are several applications you can use. I will quickly cover this process. Maybe he covered. I don't know. This was patented by Aeroprobe, where just filler rod, it may be powder or solid material. Just from the top, you will apply pressure through this tool, and it will we will deposit. Actually, this was established. One of my friend. Dr. Kumar, who was at the IISc Bangalore, he joined in Aeroprobe. He was in the patent. He patented that. Uh, Maybe I will show quickly this. There are a lot of variation there, but want of time, I'm just closing it now. This is additive. Maybe he showed or not. I am not aware of that. I will just, if you have any doubt, I will try to explain for 10 to 5, 10, 15 minutes if available, if it is provided by the organizers. So this is no aluminium 6061. If you want to build a component like that, this is the only process which will yield very good result. You will not get the same property by any method, especially additive manufacturing methods, especially when you want to deposit, because these are wrought microstructure, dense microstructure. There will not be any defects like porosity and all. But the machines now not at available in India. People, if you they develop this machine, we can do a lot of work in that process. There is a company called Meld. You can just search Meld, MELD. You can see a lot of them, their videos. They tried with different material. I have taken these pictures from the videos from their slide. Uh, just you just go through that. Properties are so good for even one advantage. Other advantage is, no, if you have a crack in a propeller like this, you cannot throw it out. So in that case, you just deposit certain material, do some machining, use it. So that they have proved this with a very good properties now. A lot of application comes into picture now. I just go through this. Yeah, uh, this I hope that he covered. If not, he will come again tomorrow. There is a topic I saw, sustainable practice in solid state. Maybe he will be covering that. This, because of that want of time, I just skipped. Bear with that. Uh, Again, this is my center. Thanks for the opportunity again, for the organizers. Feel free now to interact. Now, if not possible today, you can still visit my center in my institute. Um, Thank you very much.
My sincere thanks to Dr. A.K. Lakshminarayan sir for delivering core concept of wire arc additive manufacturing and friction-based additive manufacturing with a lot of research support. Thank you, sir. Now the
Thank
session is open to audience to clarify your doubts. Participants, you can clarify your
So if
doubts
you have
with our
any doubt,
experts.
you can post it in the chat. Yeah, you can also ask. It's not a problem. Any material related, how to proceed with any research ideas or anything. If you want, this is a rare opportunity. You just make use of it. If you have anything related to what kind of research you can start, those aspects also you can ask, or anything related to material, that also you can ask. If you have any doubt, you can just post it in the chat so that I will read one by one. Or if you are ready to ask here itself, also you can ask. No, I'm not getting anything. Okay, then it's fine. So my email ID is there at the bottom. Just you can contact. Just put a Google search. My name will come. You can ask. You can just contact.
I think no clarifications from participant side.
Okay, then no problem.
Okay, sir.
Okay, next speaker is ready or?
Yes, sir. Next session 8 at
Okay,
7:30 it will be started, sir.
okay, you'll have break.
Once again, I thank Dr. A.K. Lakshminarayan sir. Sir, thank you very much, sir.
Thank you very much.
Yeah.
Whether Dr. Daniel handled this solid state or what?
Surfaces, yes, surface properties.
Only
Surface processing. Yes,
only
sir.
friction,
Cover the
sir.
surface. Yes, sir.
Not other process. He didn't cover.
Not other process, friction-based additive
Oh, okay,
manufacturing.
okay, 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 okay. Maybe I will.
With the metallurgical, he has covered with the metallurgical support.
Okay, okay, okay. Thank you
Thank,
all. Thank you. We'll meet some other time. Okay, bye, bye.
thank you, sir. Thank you very much.
Okay.
Next, we have Dr. Sabarinathan Palaniappan, expert for the session 8. Dr. Sabari, sir, are you here?
Yes, sir.
Yes. It is my immense pleasure to welcome our session 8 expert, Dr. Sabarinathan Palaniappan. He has received BE Mechanical, ME Manufacturing, PhD Mechanical from Anna University. He has 5 years of teaching experience and 8 years of research experience. He has published 72 peer-reviewed articles with 20 plus Q1 articles. He has worked as a research fellow under government-funded project with the grant of 75 lakhs. Also, he has developed a research laboratory for recycling and reusing of industrial ceramic waste. He has received Best Paper Award in many international conferences. His expertises are polymer and metal 3D printing, polymer composites, composite filament extrusion, topology optimization. Currently, he is taking position as postdoctoral fellow at King Fahd University, University of Petroleum and Minerals, Saudi Arabia. I welcome you, sir. Now, I kindly request Dr. Sabrinathan Palaniappan to take over the session 8.
Okay. Okay. Is my slides are visible to everyone?
Yes, sir.
Okay. Thank you so much for the organizers for this wonderful online FDP. So myself, Dr. Sabrinathan. Currently, I am working as a postdoctoral fellow in IRC Biosystems and Machines in King Fahd University of Petroleum and Minerals in Saudi Arabia. So today's session, I am going to talk more about sustainability, which means sustainable composite using 3D printing technology. Particularly, I am concentrating more towards FDM process because I am strong in this zone. So I am going to deliver a talk on mostly related to FDM process. So the session outline would be the sustainability. What is the need of sustainability? Then what are the various materials available, sustainable materials available in day-to-day life, and then I am going to mix the sustainability in 3D printing process. So I need to give basic about 3D printing process, then additive manufacturing process, and what are the different additive manufacturing they are using for sustainable product development. Then I am much more focused towards FDM process. So I am going to discuss something related to slicing software. Particularly, I am going to concentrate on Bamboo slicing software, Bamboo Studio, because Bamboo is one of the best printer nowadays. They are using for all kind of product development. So I am going to discuss more peculiar slicing softwares. Uh, uh, Apart from that, I am going to discuss more about composite 3D printing and filament extrusion, then some case studies. Finally, I am going to discuss with you two product development, which means some kind of how to make a mold and how to make photo frames like that. I'll give you some idea towards making those things. Finally, it's a scopes in additive manufacturing. So coming to sustainability, the name sustainability itself, ability to sustain to the their own needs, we call it as sustainability, ability to sustain. Okay, without compromising our with the future generation, how we are going to use the materials, we call it as sustainability. So how you are limitedly using the resources and how minimally you are consuming the resources, this and all comes under the sustainability. So the main pillar in the sustainability would be the design process and how material you are selecting for the process, which is called as sustainability. So in the main parameter will be the design, how you are making the designs. If you are making a one implant, I will tell you related to implants. Okay, if you are making on implant, how much amount of material, if you are making on titanium based implant, how much amount of material you are going to consume. The material itself costly, so if you consume less material, it will automatically reduce the cost as well as the reduce weight as well as, okay, it will increase the comfort of the patient also. So like that, how much the design, how it impacts, then how much the energy you are using for the process, the energy which you are going to use compared to conventional methods in additive manufacturing process. Most of the people telling that the energy consumption was less. Yes, of course. How much energy you are going to give? If you are making a conventional route now, the product development itself, it will goes for lot of steps: primary process, secondary process, finishing process, like a lot of steps are there. So this can be eliminated by when you are using additive manufacturing process. Okay, then the technology, how advanced technologies you are using, how you are skipping those technologies, this and all comes under sustainability parameters. Okay, so these are the main things. And also the government also has regulated some kind of uh, rules and some kind of policies they have made for the sustainability. So we call it as sustainable development goals. There are 12 sustainable development goals. Yeah, there are 17 such SDG goals are available. Among that, we are much more concentrating towards 5 goals. So 4 goals. Why we are going to much more focusing towards 4 goals means, in 3D printing, we can easily, additive manufacturing can easily fit into these 5 goals. So I am much more focusing towards good health and well-being, which is the 3rd goal. The 11th goal, which is sustainable cities and communities. Then 12th one, which is a responsible consumption and production. Then finally, partnership for the goals. So these are the 5 goals, the 4 goals which I am going to cover most. Why? Because from the 5R's principle: reuse, reduce, recycle, rethink, and repurpose. These are the 5R goals. So these 5 concepts, which can be easily fit into 3D printing, which is means additive manufacturing process. Okay, so what is reuse? So what are the material you are going to recycle or reusing is we call it as reuse. And also print form management, then encourage sustainability, which are comes under the reuse. Then reduce, which is nothing but optimizing, consuming the material which are consuming the material with minimal usage, we call it as optimizing. So we are using less material. And also for design itself, we are in the design itself, we are optimizing the material consumption. In the next session, I will show a lot of design oriented things. In this session, mostly I am going to concentrate on composites. So how to make those composite and fabrication technology only I am going to cover in this session. So during the advancement of composite printing session, I will cover mostly related to the related to the design aspect, lattice structure based one. This and all I will cover in this section. Then recycling, which is means by not only filament recycling, the plastic recycling, everything comes under recycling concept. And also educate the community about filament recycling, how to recycle those materials, everything comes under the recycling concept. Then rethinking, how you are selecting the materials, in which process you are going to use. If you are going to use bio application, so what kind of biomaterials you are going to use? If you can't directly use ASA, ABS, PET, nylon, anything you can't use for the bio application. So what are the material you are going to select? These kind of main things you should be aware when you are going to use. So if you are wrongly taken those materials, this material should be simply dumped as waste. So this should be known before using those things. Then life cycle analysis, how you are going to use these things. Then it should be a circular one. Okay, Then upcycling, which is nothing but when you are converting a sustainable material in a better way. Not in recycling, you are reusing the waste material, but in upcycling, you are adding value to the material, which is called upcycling. So you are enhancing the value to the product, which is called upcycling. So these all we are considering these things now. It will comes under these 4 goals. Okay. So what are the sustainable materials which are currently available? First one is locally sourced material. The material which you are getting within this local and which are not consumed a lot, called as locally sourced material. So this material can be used as a sustainable material. If you are making something which are locally available, we call it as local material. Then recycling. So recycling, which is nothing but when you are converting a waste material and into a useful material, we call it as recycling. So the waste, so here we consider as waste which is nothing but when we don't know how to use, we call it as waste. But when the people who knows how to use it, they can recycle it and they will convert it into useful one. So this will comes under sustainability. So then durability, then eco-friendly product, the product which do not harm to the environment, we call it as eco-friendly product. So these kind of product can be used. So then repurposing, so the product which was already used, then you can use it in some other purpose. We call it as repurpose. If you have a tire, waste tire, they are using in they have used with the tire or like ropes, they will use it as some other place. Like that, you can use in some other purpose we are using that, we call it as repurposing. Then biodegrading, the material which are automatically degrading, we call it as biodegradable materials. Automatically it will degrade. So these kind of things are considered when you are making for us sustainable products. So before going into sustainable composite, people should know what is composite. Composite, why you need to do composites. Okay, so when you have certain kind of material, you want to improve certain properties. So that kind of things you need to add certain materials, which is called you want to enhance the property. For example, I will tell you a polymer. I will tell you, for example, I will take PLA, which is a polylactic acid, which is a biodegradable polymer. I will take this polymer. So, but the problem in the PLA polymer is which is more brittle in nature. So, in order to enhance the ductility of the polymer, we are going to add certain materials. It may be a fiber, it may be a filler, it may be some kind of another plastics also. So we call it as, when you are mixing together, we call it as composite. So in order to enhance or in order to improve the property by adding 2 or more materials, we call it as composite. What is sustainable composite? Sustainable composite is just nothing but when you are adding any kind of biomaterials which are biodegradable material, we call it as biocomposite. When you are added natural fillers are automatically biodegradable. PLA, which is a biodegradable material. So this would be considered as a biocomposite. So the material, both polymer as well as reinforcement mixed together, we call it as biocomposite. The material which we are using reinforcement, which is not direct, when you are adding the reinforcement, if you are adding some kind of reinforcement, like, so if you are adding some kind of fillers into the epoxy composite, it will not be the biocomposite. And how much percentage you are going to add, this and all decides the biodegradability of the polymer. Okay. So coming to sustainable composite development, you should consider 3 main important parameters. One is already I have discussed a lot about 5R. Here I am talking about more about 3R, because 3R is, this 3R cycle is the important one for waste management principle. So I have considered reduce, reuse, and recycle. So in our thing, I am going to talk more about 3D printing technology. Among that, I am talk more about FFF technology. Normally, if you are making sustainable composite, you can use 2 routes. First route, which is injection molding process. Another one is 3D printing route. So in injection molding process, if you are fabricating a component, you should have mold and other secondary operations are required. And also the cost for the production itself, it was right. So 3D printing has some more advantages. In upcoming slides, I will discuss more about the discussion difference between the conventional as well as additive manufacturing process. So the main steps involved in the composite 3D printing towards the FFF process should be, the first step should be the extrusion of composite filament, then evaluating the properties of the composite filament, then 3D printing. After 3D printing, characterizing the 3D printed components, Then we are going to use in the end application. So what are the scopes in the polymer 3D printing would be, you can towards sustainability would be composite filament extrusion. The plastic can be recycled. The support material which are developed from 3D printing also can be recycled during triple F process. Then the particles which are the materials which they are dumping as natural fillers, you can recycle that materials also as a reinforcement in triple F process. But you can't use these kind of reinforcement in some other process like SLA or else polyjet. You can't use those materials like natural fillers. You can't use it in some other process. So this is the best method for making recycling these kind of materials. So these are the sustainable recyclable materials from 3D printing process. You can see some of the dome shaped structures. The next one is teams, which is a topologically interlocked materials, interlocked bricks you may see. So we call it as teams. The next one, which are various kind of stands and buckets and caskets, everything which are the 3D printed one, but from the recycled material. Okay, mostly the first three slides, first three photos related to clay printing. The second two, which is related to FDM printing. So triple F printing. Clay printing is also one of the best method for recycling various kind of constructional waste materials. So before going into the session, I want to discuss something related to difference between the manufacturing process. So first we need to know something about manufacturing. So manufacturing is nothing but when you are making a component or a product without with the help of main or machine or tools, we call it as manufacturing. So the manufacturing can be classified into two steps. One is additive manufacturing, another one is subtractive manufacturing. So what is meant by subtractive manufacturing? Subtractive manufacturing is nothing but a conventional manufacturing process. So in conventional manufacturing process, you need a machine and also you need a material in a bulk form. So you need to subtract or remove the material from the source material. So there is a elimination of waste, as well as you need to go for secondary operation. Like that you need to go. So it will consume a lot of time and you need a skilled labor. You need a lot of energy as well as money, everything you need to make components. So in additive manufacturing process, only thing you need is a design skilled person. If you develop the design, you can easily input the things and you can print as per the need. So it is a layer by layer printing method. The component has been producing less waste compared to the additive subtractive manufacturing process. The difference between the main the people will tell us in additive manufacturing process there is a generation of no waste like that, but it is not like that. In additive manufacturing process also waste has been produced, but it will be very very small quantity. So that waste also it can be recycled in some other process. So that is the advantage of additive manufacturing process. And also you can customize a lot of product. Mass customization is available. If you want to make a 15 mm component and also 50 mm component in a one go, it is possible. But in case of conventional manufacturing process, it is somewhat difficult. In one by one it is possible. In CNC machining it is possible, but the thing is you need lot of time you need to spend. That is the main thing. And also speed wise fabrication time, it will be less when you are comparing. I will give you one small example related to implant development. In older days the implant are already fabricated ones, and they will fix as per the ages. They will have a certain set of ranges, and they will fix it as per the need. But nowadays, based on the design, based on the scan, they will convert the scan into a model and they are 3D printing. So these are the advantages in 3D printing. So going into 3D printing, I need to discuss more about different types of printing process. So what is meant by printing? When you are fabricating a product in a print bed, which is when you are depositing a material on a layer by layer on a build plate, we call it as printing. So there are different types of printings are available. First one, which is 1D printing. When you are making a line or you are going in one direction, X direction or in a Y direction, any one of the direction you are moving or writing something now, which is called as one-dimensional printing. The second one is two-dimensional printing, which is you can print it in both X as well as Y axis. For example, the photocopy machine, we call it as a Xerox machine. which is called as 2D printing. You can print in x-axis and y-axis. We call it as 2D printing. Then coming to 3-dimensional printing. So the additional axis which we are going to give, which is the height. When you are giving height to the component, when you are fabricating a component in x, y as well as z. X, y, in z, which is called as height. When you are giving height to the component, we call it as 3D printing. So most of the people call it as 3D printing. The next one, which is 4D printing, which is called as fourth dimension, we are going to give the fourth dimension, which is the rotational axis. We are going to give the rotational axis to the print bit. We call it as sorry, not a print bit. We are going to give the rotational axis to the print head. We call it as 4-dimensional printing. So in the previous session itself, you can see there is a KUKA robot. They have used one KUKA robot and they have printed that warm parts now. This all called 4-dimensional printing. You can print the supports can be eliminated if you use 4-dimensional printing. So mostly Cartesian based printers, which are mostly used for 4-dimensional printing. Then coming to 5D printing. So when you are going to give rotational axis to the print bed as well as the print head, we call it as 5D printing. So both the time both the things are the convex and as well as the mirror kind of components which are difficult to print in 3D printing operation. So these kind of parts can be printed using 5-dimensional printing. So there is no support needed when you are using 5-dimensional printing. So coming to history of 3D printing. So people calling us this additive manufacturing are new like that. It is not a new one. It was developed in the 19th century itself. It was initially they have used only for the prototype development. But there is no development in the materials perspective. So in the 1970s, there will be not much more growth in the 1970s stages. So they have again in the recent days after 2000, they have there are a lot of research going on materials. So they have developed the 3D printer. In the year of 2000, the low-cost 3D printers have evolved a lot, because initially the low-cost printer people will normally called low-cost printer will be the FDM and SLA are the low-cost 3D printers. Why? Because initially the FDM 3D printing FDM printer rights as with the Stratasys team. So in the year of 2000 only the Stratasys patent rights was over. So after entering China entered into the market, they have developing low-cost printer. That time only they are converting these kind of FDM printers. Then there is a lot of research are started in the FDM printers. Then in the 2010 they have doing lot of research on SLA printers. Now the people they are working on volumetric 3D printing, because there will be no support. Everything which is are not required. So you are going for a hybridizing those process. Everything you can do. And also there is more research going on nowadays on sustainable materials. So that is the current trend, to use sustainable materials for making to develop 3D printing process. The printer itself, they are using the waste material. Okay, fully 3D printers are available nowadays. So there are a lot of new things are came nowadays. So why there is a reason for booming additive manufacturing in India, which is not only India, all over the world, is every industrial revolution there will be some kind of components of that. In Industrial 4.0, they have given 3D printing as one of the parameters. So why they have taken in Industrial 4.0, there is a lot of material wastages has occurred, and also there is a lot of time consumption, and also there is a need of lot of manpower. So they have involved 3D printing or automated one or self things are required. So in Industrial 4.0, they have involved 3D printing is one of the main parameters. So in 2020, the global 3D printing market was valued to be 13.78 billion. But it is expanded to 21% annual growth rate for 2021 to 2028. But in 2026 itself, it was crossed beyond 21%. This is a boom advancement in 3D printing. So coming to now, they are going to use Industrial 5.0. In Industrial 5.0, they are considering two main parameters. One is sustainability, another one is additive manufacturing. So both the things are joined together in the Industrial 5.0 concept. So if you are making a sustainable product using 3D printing technology, it will be a good thing. So you need to concentrate on both things. Now you can use those things. Okay. So before going in depth towards these processes, I am going to discuss something related to. I think most of the sessions they are covered more about different types of 3D printing processes. So I will cover with a single slide. So I am going to cover with this slide. So I am going to classify the additive manufacturing process with the type of material they are you going to use, and which form they are you going to use, and what are the energy which you are going to use. Based on that, I am going to categorize the additive manufacturing process and how the additive manufacturing process was working. It will be addressed from the coming upcoming slides. So first, initially, I am going to discuss with you what are the types of material they have used. Type of material which normally they are classified into three materials. One is polymer, another one is metal, another one is ceramic. The ceramic should be in powder form. This powder can be directly put it as a powder and they can be printed, and also they can convert the powder. It can be converted into paste, which is called as clay printing. It like a paste, and they will print using direct ink writing method or some other process. You can print the case. Okay. In metal, they are using different process, both powder as well as wire. They use powder by direct energy deposition or some other process. DMLS, everything comes under powder form. In wire, we will use, you can use for direct energy deposition as well as uh, wire additive manufacturing process. So coming to polymers, the polymer can be used in different forms. It should be used in polymer, it should be used in powder form, liquid form, wire form, and pellet form. So you can use various forms of polymers. If you use powder form, you can use SLS, selective laser sintering. You can use powder form nylon. Mostly they are using nylon for SLS 3D printing process. The part finish was good. The layer resolution also good. You can use most of the engineering grade application. You can use powder based technology, which is SLS based technology. The next one, which is liquid. In the liquid, they are using in various processes such as UV curable resin. They are using for vat photopolymerization, and polyjet printing. They are using photopolymers. They are also UV light as a source. Then binder jetting. They use some additional binders. If you are using epoxy, there is an hardener is available now. Similar like that, there will be a binder. If you are using binder now, they will use binder for curing, which is a hardening of the polymer. Then wire form. Wire form, which is nothing but a filaments. You already know. All the institutes they are having FDM or a triple F based printer. This is a fused filament fabrication printer. So the concept is very simple. You are going to melt the filament and they are going to deposit in a respective shape which you are want. Okay, so filament will be various types of filaments are available. PLA, ABS, ASA, a lot of filaments are there. I will show you. I will tell you about those filaments and properties, everything in the coming slides. So then finally it is where granules. Granules, which is currently they are using in lot of industries as well as component development, industrial grade application. Also they are using direct pellet based printing, which is called fused granular fabrication. Here also the heat as a source. Instead of putting a wire, you can use the granules as a source material and you can print. So coming to the energy, if you are using heat source, mostly the heat source, all the thing they are converting thing into a heat. Energy should be converted into heat only. But in fused filament fabrication, directly you are heating the coil and you are melting the filaments as well as polymers. Similar to FGF, also the same phenomena they are following. In DLP, SLA, as well as binder jetting, everywhere they are using UV crosslinker as well as UV gun they are using to cure the material. Then direct energy deposition, they are using arc as a source. Then plasma for direct energy deposition, laser as a source for DMLS, SLS. They are using arc laser as a source. In electron beam melting process also, they are using electron as a source. So this is the difference between the various additive manufacturing process. So coming to plastics, I am concentrating more about plastics. Why I am going to concentrate on plastic? You can usually convert the material into the required form because the energy consumed for plastics is less when you compare to the metal. So the facility availability also easy when you are comparing to plastics when compared to the metal. So the people nowadays they are started to working on various kind of uh, polymers. Here I am going to concentrate more on thermoplastics. Why I am going to concentrate on thermoplastics means I am going to discuss more about filament extrusion technique. So I am going on thermoplastics. In thermoset also you can use to make a composite materials because in thermoset based SLA printers, they are using epoxy based resins only. They are using for 3D printing. So when you mix some kind of particles using these kind of uh, thermoset resins, which are UV curable resins, you can make composites. Then elastomers, which are nothing but a rubber based materials, and urethane based, which is a TPO, which are comes under urethane, which is a polyurethane, which are absorb more energy when compared to other materials. Coming to the pyramid, you can easily consider. You can see the material which are come under the base material, which are very costless, and also that there are called as standard plastic. So they use for the general purposes because it will does not have a good strength, but it can manage minimal load. But when you go with the green one, which is called engineering plastics, so the material which can withstand which more load, which are nylon, polycarbonate, which are the engineering grade polymers. So these are mostly used for engineering application. But the next one, which is the advanced engineering materials, which are nothing but materials which are used for the advanced process, like if you are making an implant. Okay, it may be a cranial implant, which may be your bone blade, or else you can use any kind of uh, some other implants. You can use PEEK, polyether ether ketone, which is one of the most used implantable material because it is biologically inert and biocompatible material, and it will not. It has a less stress shielding effect. So these are the advanced engineering material. So the final one, which is would be the thermal stability, imidized material, which are high thermal resistant materials, altum, everything which are comes under the high temperature resistant materials. Okay. So, I am going to discuss something related to healthcare application. So these six process, among these six process, this five process mostly used for the healthcare application. So I will discuss this more in tomorrow's session. I will discuss this with respect to the healthcare application. Okay. So coming to material jetting, I am going to discuss something about what are the process involved in the classification of the additive manufacturing process. So in material jetting, which is nothing but a polyjet process, we call it as material jetting. When you are jetting the material, it will comes out as a spray. They are using two approaches. One is continuous approaches, another one is drop on demand approaches. So in this process, they are jetting the material like they are spraying the material into the print bed, and you can use UV laser source as a curing medium. So every time the material will come to and fro motion, the polymer will come along with that UV light also will come. So I will show some of the videos related to this material jetting. So this kind of material jetting, you can use multiple materials like polyjet materials you are using. You can use Berro, Agilus. These are different grade of material they are using for polyjet application. In tomorrow's session, I will discuss more about this polyjet printing because I am going to discuss more. This is one of the. These are the simplest steps. You can see this video. So initially, the material was jetted from the nozzle. These are 8 different nozzles are there. The material which are jetted in a the green light, which is an UV light, which are curing the material. So this is one of the example for polyjet. So mostly they are using photopolymer. Based on the photopolymer, they are making different density, different shore hardness, different hardness, everything they are making. So these are the one of the finest technology for making cadaver kind of things. Tomorrow I will show you those things. Then powder bed fusion. Powder bed fusion is mostly used for metal as well as SLS. DMLS as well as SLS are comes under powder bed fusion method. In powder bed fusion method, using powder as a material, the powder which are filled in the build platform, every time the powder will come and to and fro, it will come and go, and the laser source will, which will fall on the print bed, and the material will be based on the design which we are given. The component was fabricated. Tomorrow I will show you some of the lattice structure based material which are 3D printed using DMLS technique. So this is some of the example for making how the powder bed fusion is working. Here they are printing titanium material. This is a powder based one. So the component was 3D printing. This is the secondary process they are using. So during during DMLS and SLS process, the problem is after printing your component, the secondary operation, which is the removal of those supports, which are some complicated profiles. It is difficult to remove the supports. Recently we have 3D printed one lattice structured material, which is a krigami based material. So the material which was filled inside that structured one, we are not able to remove those materials, because removing those kind of materials are very, very difficult. But when we are using polyjet technology, there will be water washable supports are there. So you can put it in the water itself, it can be removed easily. So the materials which are used mostly in powder bed fusion should be nylon for SLS, then stainless steel, titanium, aluminum, cobalt, chromium for DMLS process. DMLS mostly they are using titanium and cobalt, chromium, because these materials are mostly used for the implant development. Then SLS, selective laser sintering. This is polymer based method. Mostly they are using nylon as a source material. Similar to DMLS process. Here also the laser as a source for the fabrication of the component. Once the part is printed, every time the roller will move excess material to that side, and it can be collected in the collector tank. This is an example for the SLS process. And selective laser melting also similar to that. I think some of them has already shown these kind of videos. I think so. I am skipping these videos. So DMLS, EBM also similar to that. So I am skipping these parts. I think most of them have covered these things. Okay. So coming to my core area. So guys, okay. So I'm going to discuss more things related to extrusion-based 3D printing. So the extrusion-based 3D printing can be classified into 3 different categories. One is FDM, another one is FGF, another one is clay printing. The first one, which is called as FDM printer, already I have told you that the material which they are using for this FDM printing is filament. So they are heating the filament using the nozzle, and they are printing the material on the print bed. So mostly they are using FDM for the prototype development. But nowadays FDM can be used for making implants itself. So they are using lot of things related to FDM based printers, using peak material. They are using there are a lot of materials are there. Polymer is there. There are a lot of materials, composite materials are PLDLA based calcium composite materials. There are a lot of materials are there. So they are using FDM based printer itself, and they are fabricating lot of implantable materials, bone scaffolds, lot of things they are using for fabrication of implants. Then fused granular fabrication. The advancement of FDM process, we call it as FGF, which is called pellet based 3D printing methods. There are some limited printers are available for the fused granular fabrication process, but the thing during fused granular fabrication, the raw material should be in the pellet form. They are using screw type of extruders, and also we have used piston type also we have used for fabricating pneumatic based setup also we have used for fabricating film pellet based 3D printing parts. I'll show you those things in the upcoming slides. Then the problem during the fused granular fabrication is uh, the the nozzle size was very big. Similar to clay printer, the nozzle size was very big, so the layer resolution was very less. So after printing, the surface roughness was very high. So you need to go for the secondary operation to in order to improve the surface roughness. So the roughness was not good. So there are some kind of process of that. So to improve the surface finish of the component, you can go with this secondary processes. You can increase the surface roughness. So you can eliminate those things, and you can go this kind of texture process. Then clay printer, which is nothing but a paste printer. We call it as clay printer. You can make your own slurry with the record rheology, which is nothing but viscosity of the material. You can make your own slurry. Then you can put it into your extruder head, and you can make your own design, and then you can fabricate your component. This is the simplest difference between these three printers. Similar to the clay printer, only the bio printer is also working. In bio printer, they are using the different types of injection. Bio printer also working on the extrusion based principle only. They are using three different principles. One is pneumatic, another one is piston, another one is screw based extrusion technique. In bio printing, the biopolymers are loaded into the extrusion head. Extrusion head may be maybe the paste format, or else they should be in ink format. After loading the material, if it is in a paste format, now you can cure it in furnace. If it is in ink format, the curing strategy you should follow. You can mix your own curing agent along with the polymer itself, or else you can add in some kind of curing agent. After printing, you can use some kind of cross linker. Like that, you can use. So these are the difference between the extrusion printing. So in extrusion printing, I am much more concentrated towards fused filament fabrication process. Nowadays they are doing all kind of components using fused filament fabrication process. You can make your own filaments, not only polymers. You can make anything which are in the filament form or else in a paste form. You can fabricate the component using extrusion based technology. You can fabricate your own food. You can fabricate your chocolates, footwears, everything. Recently, I have my own 3D printed shoes. It is available in the internet. You can adjust your cross, you can measure it, and you can adjust your cross section, and you can put it now. You can print your own footwears. Okay, so there are a lot of things nowadays advancement in fused filament fabrication process. The main principle I have already discussed more about it. It has a heating unit. You have filament, and it has a print bed. Based on the design, you can print the model. This is the simplest discussion about fused filament fabrication process. In fused filament fabrication process, the main thing is materials. They are using only thermoplastics. Why? Because they are using heat source as a material. So the thermoset which are having a cross linker, so you can't change their shape. But thermoplastic, you can regain the shape. If you melt it now, you can reform it in different shape. So thermoplastic is mostly used as a feedstock material for the FDM process. Here I am discussing more about PLA, ABS, pitch, nylon, HIPS, PMMA, and the composite filament like wood, ceramic, and metal based PLA filaments. But the problem, I am discussing more things towards the coming slides about materials where you can go into use. I am already discussed these things. There are polymers in FDM process. They are mostly using one is hard plastic, another one is flexible one, another one is high performance plastic. The hard plastic, which are nothing but a PEEK, PLA, the metal which are have high rigidity, we call it as a hard plastic. The flexible polymer, which are nothing but TPU, polyurethane based material, which are having high flexibility. So we call it as TPU. So the main components in 3D printer should be the frames, print head, and the print bed, which are the main components in the 3D printer. So the components which are mostly in all the printers, these three parameters are fixed. Why? Because in 3D printing, the rotational axis, that's not a rotational axis, the X, Y, Z coordinates are the main thing. So they have using three main parameters. So what are the defects which are occurring during FDM processes? Warpage. Warpage is one of the main defects which are occurring in the 3D printing process, because if you are going with the high thickness component, the adhesion between the print bed with the polymer is not good, means there will be a chances of warpage will occur. So in order to eliminate these things, we need to reduce the large flat areas, we need to remove the sharp corners, and also we can use a high thermally stable material as a bottom layer. So types of FDM printer. So nowadays they are using different types of FDM printer. The first one, which is single extruder based printer. There will be a only single extruder. We call it as single extruder. Then the advancement, they came up with the dual extruder. They come up with the AMS unit. We call it as a there is a lot of generation of choke material, which is called as waste during printing itself. If anyone have idea about bamboo printer, you can see the first image, which is called as a bamboo A1 mini, which is the normal FDM printer which is connected with the AMS unit. So there will be a single extruder with the different materials. You can change every time, it will change. If you are painting, you can change that paint brush with the water you are dipping, then you can again painting like that. If you are printing, you want to change the color now, they will automatically change the color as well as the material. But there is some process is there during slicing itself. You can do those things now. It will eliminate those things. Then you can print multi materials. Okay, using a single extruder itself. Then there is an advancement came. All the printers. I am discussing more about bamboo based printer, because this is that printers are nowadays ruling the FDM market. So X1E, X1C, X1C, all are comes under single extrusion head, and also the X1E, which except A1 mini, all other combinations which are coming of the AMS unit, which is the second concept which I have discussed. Then dual extruder, which is nothing but a two extrusion head. You can easily print multi materials, which is why you are going for multi materials means, if you want to make a shape memory based polymers or advanced polymers, means you need to go with a dual extruder. Okay, and also the waste elimination can be cut out using this kind of dual extrusion head. So recently the bamboo has launched H2D printer, which is not H2D printer. So that they have developed a method. They use two different nozzle, and the print bed size also bigger, 300 mm, 300 mm, 300 mm, bigger bed size. You can see the second image. You can see there is a two print heads, two nozzles are there. So it can be used for making two different materials using dual extrusion. Then there is an advancement of this dual extruder itself. You can use single extruder, then they will go and change the extrusion head. This is called Prusa XL. This printer is nowadays this also commercially used nowadays. Then the in bamboo they are launching H2S. They are going to launch in the upcoming month. They are using a single nozzle, and they are connected with a different nozzle. They will come and change, like if you have seen this some kind of CNC, they will come and change the tool head like that. They are changing the tool head automatically. So this is one of the advanced process. If that printer is came now, it will be a very advanced process. There automatically you can print with multi materials. Okay, so coming to the motion system, they are using, already I have told, Cartesian based XYZ. They are using straight lines. We call it as XYZ Cartesian based 3D printers. Then core XY, now they will only move on XY direction. The print head as well as the print head, it will only move in XY direction. We call it as the print bed will not move. We call it as the core XY thing. Then delta printers, there is a tilt movement you can give into the print extrusion head, we call it as delta based printer. Then polar printer, there is a rotational axis which is given to the print bed, we call it as polar printers. Okay. Then there are two types of extrusion is going on in the FDM printer. One is bowed and extruder, another one is direct drive extruder. In direct drive extruder, the filament was automatically pulled down by the machine itself, but it was more very suitable for flexible materials. If you are using bow down kind of extruder, means the material will not be automatically pull out into the machine. There will be two screws on that. In bow down extruder, it will not be pull down automatically. Motor itself pushes the filament through the PTFE2. But in the kind of direct drive extruder, the filament was automatically extruded by use of the direct drive unit. So the direct drive has somewhat advantages when compared to the bow down type. Then based on the build volume, if you have a smaller bed size volume, we call it as desktop printer. When you have a large build volume, we call it as a industrial grade or a large format 3D printers. So coming to the process in 3D printing process. Okay, so in 3D printing process, everyone has an idea. So you want to make the idea into a product. So you want to make a exact mimic of this component. Okay, so if you have the idea, you are measuring all the things, and you are altering something. Like if you want to make this as a flexible one, another one which is a hard one. So you have the idea in your mind. Then the idea need to be converted into design. So the design should be converted by using various kind of software such as Fusion 360. Fusion 360 is the best tool to convert your idea to design. Nowadays, you don't need a design software itself. AI itself enough. ChatGPT and other lot of softwares are there. Using those software, you can give your ideas, and you can convert your idea into a component directly without knowing any kind of design knowledge. Without design knowledge, you can directly make your designs. Okay. Then after making your design, the design should be readable with the machine. So the machine cannot directly understandable with the direct format, but nowadays that is also possible. You don't need to slice the things. The machine itself automatically slicing nowadays. So there will be a need for slicing. The slicing, which is nothing but converting your design into machine readable format G code. We call it as slicing. Okay. There are a lot of slicing softwares are available. Open source software, people tell us Cura. Cura is mostly supported for reality based printers. But the thing is, you should know about Orca slicer. Orca is the universal slicer. You can use it for all kind of printers. ORCA. Orca is one of the software. Then after slicing, you need to put the design into the 3D printer. After during 3D printer, you should have some knowledge about 3D printer. After 3D printing, the part should be removed, and it will go for secondary operation like support remover or surface enhancement or a surface roughness reduction kind of secondary operation. Then the quality can be analyzed with the design matchable. Your component was fabricated with as per the design or not. You can check all the things. Then the product should be given to the customer end. So during 3D printing operation, you are getting lot of design knowledge. Mostly, I think they are all our faculties. So if you I think interdisciplinary faculties are there. I think so. So 3D printing is not dedicated towards not only for the mechanical engineers. It is dedicated to all the departments. Why? Because the application wise, you can fabricate antennas. Okay, you can fabricate building. So anything can be fit into 3D printing. Okay, so design engineering knowledge is required. Machine learning based optimization is going on. So that skill you need. So process parameter, AI based slicing processor nowadays came. Okay, so the machine itself nowadays automatically slicing based upon the material. You need to just give the design material. Then automatically the material, the complexity of the design, the material itself automatically they are slicing. Okay, so this and all nowadays slicing, which is nothing but I will tell you in depth about the slicing proper things in the upcoming slides. So there are a lot of printing parameters which will affect the part quality. The slicing are the important parameters. During slicing, the parameter need to be set for the parts. So that part decides the quality of the product. So there are lot of parameters are available. I think most of the people has covered these parameters, I think so. So I just read out those parameters and I will skip to slicing part. Okay, in those part I will discuss more about these parameters. The first one, which is infill density, which is nothing but you are developing a component based upon the density, based upon the filling of the material. We call it as infill. Okay, how much volume of material you are going to fill? 10% infill means you are going to fill with the material product with the 10% of the material. We call it as infill density. Okay, so it will automatically reduce that, because it was fully with the pockets now. It will automatically reduce the print time, everything it was reduced. But the thing is, if you reduce the infill in density, the strength was reduced because the material was automatically reduced. Okay, then infill pattern. uh, Infill pattern, which is nothing but a structure or a way or a track which you are going to use print. We call it as infill pattern. When you are making into a single direction, single layer of infill pattern, we call it as mesh. You can take a single layer and you can take the single layer. Now it will be look like a mesh. I will show you in the coming slides. I will show you those things. Then there are other parameters like layer thickness. Here I am showing only 3 layer thickness. One layer thickness, which is nothing but the material with how much the thickness of the material for each layer. We call it as layer thickness. So here I am going to here I am showing only 3 layer thickness: 0.1, 0.2, 0.3. Nowadays you can go up to 0.08. You can go beyond 0.1 also available, and that and all I will discuss in the upcoming slides. Then support. There are a lot of supports are there. When you are printing with complicated profiles, you need to support materials. So the support material should be the support can be generated automatically, or manually you can select the materials. So the support should be a standard one, or else it should be a tree one. If you have a tree one, you can, like a tree, you can place it wherever you want. You can give the supports. It is in manual form or it's automatic one. Then printing orientation. So what type of material you are going to fabricate decides the printing orientation. If you are fabricating a tensile sample, you can't print it in a 0 degree. Why? Because if you print it in 0 degree, if you are giving tensile load, if you give the load in the 0 degree direction, the layer will be easily peel off and it will be break down easily. So based upon the loading conditions and what type of application you are going to use, the printing should be selected. Mostly you can use for 90-degree printing orientation, it will be good. So it will, or else you can change the print part, like flat, upright, on edge, like that you can change your print orientation. Okay. So coming to the slicing parameter, so there are a lot of parameters are available. When you are going to use a 3D printer, you should think what are the components in the FDP printers. Okay, the first one we are calling the main 3 print parameters. The first one is a bed. Why we are considering printing bed now? The printing bed decides the quality of the product. If you are printing a component for a 2 hours print now, if the component will, the high chances of failure of components are occurring. There is a chances of that based on the complexity. The chances of failure occurs. So if the product was not fixed properly in the print bed, it can automatically move on, or some other failure will occur. So the print plate should be good. In olden days, they are using some kind of Fevikwik or Fevistick as a, for bed adhesion. They are using something called adhesive medium. If the one layer is over, now they will put again. They are putting adhesives. But if you are making some complex, some good products, now you can't use this kind of adhesive again and again. So there is a revolution in the print bed. So they are using different types of build plate. The first build plate, which is called textured plate, which is a fully stainless steel based plate. Mostly the surface should be the adhesion between the print bed was very good. The textured plate. Then next one, which is smooth one, which is a flat sheet based one, which is called the engineering plate. This is very smooth, PA based plate. It can withstand high temperature. So this is polyether IMI polyethermide based print bed. Polyethermide coated stainless steel. Sorry, not a polyethermide based material. Then combination of polyethermide in one side, another one is textured plate. That is one type of plate. The next one, which is the 3D effect sheets. if you paste these kind of sheets on the print bed, and you can print your component. So the texture which are directly comes under the components. If you want to this kind of starry surfaces now, you can use these kind of things. If you want to galaxy surface now, you can use these kind of sheets. So this kind of sheets you can easily it is like a magnetic based sheets. You can just put it in the print button and automatically absorb. Okay, these are the different print plates used in the printers. The next one, nozzles. Most of the printer they are giving with 0.4 mm nozzle. But if you are going to print with composite filaments or pellets now, you need to increase the nozzle size. If you are not increasing the nozzle size now, there will be high chances of material blockage inside the nozzle. The nozzle should be 0.4 mm, very, very small one. If you are adding some kind of wood-based fillers or fibers, anything you are adding into the composite material, it will automatically deposit inside the nozzle unit. So you need to increase the nozzle. If you want to smooth surface finish, now you want to go with a 0.2 mm nozzle. So based upon the nozzle size, your part quality will be decided. Then coming to the layer height. Here I have selected 0.2 mm nozzle. Okay. I have selected 0.4 mm nozzle. In the 0.4 mm nozzle, you can go up to 0.08 mm. In a conventional printer, you can go up to 0.1 mm. Normal printers, but in this case, you can go up to 0.028 mm. If you use 0.08 mm now, that printing time it will take a lot of time. It will take to print the component, and but the part quality was very good. You can't even identify which part it is like that. Okay. Then infill pattern. I have already shown some of the infill patterns. So these are the infill patterns which they are using. So infill pattern, if you are adding this infill pattern without any shell wall or wall thickness, if you are not giving wall thickness now, it will looks like a lattice sample, lattice structured sample. Mostly these lattice structure samples, except all are comes under this gyroid is a TPMS based structure. Apart from that, everything which are comes under planar based lattice structure. Okay, so why you are giving this kind of infill pattern to the sample now? If you are going for an energy absorption based applications. Okay, if you are going to give some kind of sound absorption panels like that, now you can use these kind of patterns. It will absorb more energy. Like that, it has several advantages of using infill patterns. Then materials. So material is the main main material thing which you consider for a FDM process. There are a lot of materials available. The commercially used material will be PLA, ABS, PEDS, PLA, ABS, PEDS. 1 minute. Okay, PLA, ABS, PEDS, and TPU. These are the most used material for the 3D printing process. But the problem is every material which has certain kind of okay. Apart from this commercial material, I am discussing something called new material called PCTG. Another one is called ASA. The people mostly use PEDS, but compared with PEDS, PCTG has a more flexibility and also easy to print, and also it has a heat resistant, chemical resistant, and also it has comparatively compared with PEDS, it has high impact resistant as well as processing also easy. So PCTG is nothing but polycyclohexyl dimethylene terephthalate glycol. It is a glycol family material only. So it has it is nowadays they are using this kind of printer. If you want these kind of filaments now, you can contact AZURE Azure Films. These are the supplier for these kind of filaments. Then ASA is a good material for fabricating UV stable components. For some of the printer components, like in UV printer, SLA based printer, nowadays they are printing with the ASA material because it has UV stability. And also, if you are making, I will give you a simple example. If you are making some kind of weatherproof application based material or sun shielding kind of application, you can use ASA, which are having UV stability and also have a better strength than ABS. So these are the advancement of advanced materials nowadays they are using in the 3D printing process. Then ironing. In some of the it is in ironing is the one of the parameter they are mostly used in FDM printers. Ironing, which is nothing but without a material, the nozzle can be heated and it is moving on. The part dimension should be like this now. The extrusion head which is moving on the same profile, already it is printed the same pathway without material, it was heated and it is ironing, which is called ironing. Okay, so this ironing can be done on all with different places like top surfaces, topmost surfaces, in all layers, everything we can done. So if you do the ironing now, the surface finish was good, but not in the outer boundaries. In these zones we can't do ironing. In the print direction we can do the ironing. Okay, the most covered area we can do the ironing. So these side areas we need to do with secondary surface finish process only. Okay, then we are going for the support material. I have already told that there are two different support. One is called normal, another one is auto. They are using normal support, which is the first one, which is a normal support. The next one, which is a tree support, which both are related to automatic one. If you want to manual one, you can use a single tree, and you can put like a one by one. Here there are 7 to 8 trees are there. Instead of that, you can put only 3 trees, like a 1 2 3 like that. One corner one, and center one, like that you can print. Okay, this is one of the thing. The next one is support material. So support material. This is now I have discussed about types of supports. Now I am discussing more about materials which are used for supports. Okay, there are a lot of support materials are available. PLA support, ABS support, like that they are giving from the supplier. But the thing is, mostly they are using PVA, which is a polyvinyl alcohol, which is a support they are using. These supports are water washable. You can easily wash it and you can peel it after printing is done. Okay, if you don't want this kind of support material, you just want to print a material without, but you need to remove the supports easily now. If you are printing in PLA, you can use bed as a support material. Okay, you can use the raft or a support material. Select those materials as a bed or some other materials, because the compatibility between the bed and the PLA is very not good. Okay, so you can usually remove those parts with once it is printed now, you can remove those parts if you don't want this kind of supports like PVA kind of stuff. Then challenges during 3D printing process. So normally the main problem during the FDM process is the surface quality, and also during printing there will be high chance of clogging. So these are the main challenges you face during 3D printing. I will cover some things related to composite 3D printing, and this one I will show you the real time things. Okay, so then coming to performance assessment. If you are making a composite filaments, okay, if you want to evaluate the performance now, this is the performance assessment. If you are conducting exam now, you will give you the question paper and they are assessing the student like that. If you assess the printer as well as the material using this performance assessment kit, we call it as a template. This template you can measure the first, you can measure the stringing effect. You can go up to 80 degree. Based on that, if it is support is secured, the material is stably is there, not like that. You can measure it using this stringing effect. Oh, so not a stringing effect. This kind of stringing only. Right? Okay. Then ridges. Okay, ridges which are I'll show you. This one is ridges. Stringes are this one. Stringing is cone only stringing. Okay, sorry, I have discussed it wrong way. Okay, ridges which is measured by using this kind of beam. Then clearance can be measured by using this kind of holes. In this portion it was the opposite side it was available. So the clearance can be covered by, there will be a small dot of circular portion is there. So the clearance between 0.1, 0.2, 0.3 like clearance is there. So you using those things you can measure the clearance of the material. Then cone using this cone you can measure the stringing, the different cone height and the diameter of the cone based the stringing can be measured. Then based on the Benji model, you can you can see the how small component can be printed, can be measured. Then this 45-degree bridges can measure the accuracy of the printed component. So this is the performance assessment model for and also there will be a 0.2 mm layer height, 0.4 mm layer height, 0.6 like that it is available. So based on that the surface quality also assessed. Then coming to composites. How much time is there, sir? Hello?
Sir, up to 9 o'clock we can.
Up to 9 o'clock we can go.
Yes.
Okay.
Still
So
we
coming to
have
composite 3D
15.
printing,
Still we
yes
have
sir,
15 minutes. 15 minutes we can take, sir. 10 to 15 minutes.
10 to 15 minutes. Okay.
Thank you.
Okay, thank you. So coming to composite 3D printing, I have already explained more about composite 3D printing. So when you are mixing, you want to increase some kind of properties, we call it as composites. So I was skipping this part. So coming to the benefits of composite printing. So when you are making some kind of some peculiar property, if you want to improve the some kind of peculiar property means, like you want to improve the mechanical properties. Okay, then you can go for composite printing. So you in order to enhance the thermal properties, you can use that. Then you want to enhance the biodegradability and biocompatibility in order to reduce the surface roughness. People tell us if you are adding certain kind of reinforcement, it is not possible to. If you are adding certain kind of fillers, the surface roughness was reduced like that. It is not. If you are adding those things now. If you are adding certain kind of particles, it will reduce the surface roughness. But if you are adding certain kind of plasticization, the surface roughness was reduced because the plasticity was improved. Then the melt flow was good. Then the surface roughness was reduced. Like that, based upon the need and the application, the the composite 3D printing was used. So in composite, there are two main elements. Are there? One is polymer, which is a matrix. Another one is reinforcement. The reinforcement may be a fiber, particle, or nanotubes, or wires, or continuous fiber. Anything which is which any form it is available. Okay. But the thing is, based on the rule of mixture, we are mixing these things with the polymer, and we are making our own filaments. Is my slides visible?
Yes, sir. Visible.
Visible. Okay. Okay. So coming to the polymers, there are a lot of polymers are available. So based upon the property, this is the simplest data sheet. You can easily set the limit of the how much nozzle temperature you are going to give and how much bed temperature you are going to give. Based upon the application, you can select the polymer. So this is the simplest thing. If you want a tough material, now you can go with nylon. Okay. You want to have a high abrasive resistant, which is tear resistant material, now you can go with the ABS. If you want to flexible material, now you can go with the TPU. If you want to biodegradable material, now you can go with the PLA, PCL, some other polymers are there. Okay. If you want a UV resistant material, now you can go with the ASA. Like that, based upon your end application or the need, you can select your polymer. Okay. Okay. I will cover these things in the next session. I will go with the activity. Okay. Okay. I will show you one of the activity. So this is the litho pen maker. So those who are want to make your own litho pen, you can simply you can upload your photo and you can make your litho pen using just there is a simple steps. It's a page called It's Litho. Okay, you can upload your image and you can convert your image into this kind of litho pen by varying these kind of grayscaling images. And also you can add some kind of borders. If you want to make it as a border, now you can do border. And you want to make add lamp, now you can add lamp. Okay, you can see in the begin these things there is a lamp is available. Okay, so this is one of the thing you can use litho pen. The next one, you can use your own photo frame. Okay, so this is the thing available in a bamboo slicer itself. You can use your photo and you can upload it in the maker's world, and you can use the configurations such as thickness of the model, width, everything you can select it. Then you can use hooks, with hook and without hook, or you need what type of hook you need, and the diameter, everything you can fix it. Then again you can go coming to this another process called text. You can add any kind of text, whatever you need. Like that you can add any text, like that you can add. And also you can add it can be superimposed, or else if you want to the image should be come out or backside, it can be done using these kind of things. Okay. Okay, these things I will cover tomorrow. Okay. Yeah, thank you. So tomorrow I will discuss more about how to make a mold also. Your own mold also. It is I will discuss those things. So, any questions?
So my sincere thanks to Dr. Sabarinathan for providing detailed research informations regarding composite 3D printing and its sustainable reach. Thank you, sir. Now the session is open to audience to clarify your doubts. Participants, you can clarify your doubts.
Sir, good evening, sir.
Yes, sir.
Sir, for a person who has started with introduction to an FDM process, would that person be more comfortable with starting with slicing software like Cura, or would you recommend them to go with the Bamboo software uh, as they start?
Cure is very, very easy, sir.
Okay, sir.
Bamboo is very, very easy, user-friendly software.
Okay,
Cura,
sir.
if you need Cura, now you can use it Cura for only Creality kind of printers. But in Bamboo printer, you can use all the stuffs in an easy way. Okay. Uh, I will show you. This is one of this is the Bamboo software. Okay. Is it visible?
Yes, sir. Yes, sir.
My screen is visible. Yes. Okay. So you just select your quality, the strength, that speed, that support, everything. If you finish everything now, just preview, then slice. That's it. This is a very easiest tool. You can use this Bamboo everything. Initially, I started learning from the Cura only. That time I am not aware about Bamboo software. But recently, last 4 years, it was very good.
Sir, there is some noise actually. Another
I
participant's
didn't
mic
get you.
actually was not able to hear
There is
you guys.
I didn't get your voice properly. There is a sound. There is sound.
Sir, there is interference in the audio actually.
Can you put it in a message? Huh?
Sir, if the hosts can just please mute the mic of Mr. Mohan Sir Pardeshi, I could listen to the answers
It's not
actually.
audible for me because there is a big sound is coming. I don't know where it is. Can you change the layer with this creating an image? Yes, it is possible. Each layer we can change the layer thickness. It is possible. You want to know how need to change those things?
Any other clarifications?
Hello, good evening, sir.
Yes, yes, tell me.
Session was very nice, sir. I want to ask one question. Just tell me the percentage of mixing of material. Suppose we are using base material as PLA. So,
Okay.
how much is the percentage of material that can be mixed or that can be possible to make the filament? Then we can build a part.
Okay.
Are you getting my question, sir?
Yes, I understood. I am going to show you some slides. I
Okay.
have not yet covered those things. That's why I am taking slides. Okay. My slides are visible now.
Yes, sir. Yes.
Yes, sir.
Okay. So this is the extruder one. Okay. So normally, if you extrude some components now, it mostly I will prefer not go beyond 10%. Why? Because I have faced a lot of issues. Okay, tomorrow I will day after tomorrow session I will discuss these things. In a fast way I will discuss all. Okay.
Yes, sir.
If you increase beyond 10% now, there will be
Yeah.
high chances of clogging occurring in the nostril. And
Yes, sir.
also
Because
the particle
yeah.
sizes also plays a important role. Okay, if the
Yes.
particle size is more than 50 micron, okay, because your nostril size is 4 microns, I think so. Okay, 40 micron, not a 40 micron, 4 microns. Okay,
Yes.
so if you increase the particle sizes also, it will be chances of clogging is there. So if some condition there will be three particles are agglomerated, and if it comes together, and it maybe chances of clogging in the nostril also, chances are there. So try to go with less than 10 percentage, or most maximum go with 15%, not go beyond 15%. If you go beyond 15% now, you should definitely change your nostril size. Okay,
Okay. Okay, sir. Because I have
if you
tried.
increasing your nostril size to 0.8
Yeah.
mm now,
Yeah.
you can go with some uh, 20 to 30% also, it is okay,
Okay. Because what
but
happens,
it will reduce
sir?
the strength.
Yeah. Yeah. Because I have tried with Moringa wood fiber with PLA.
Mm.
So the filament is
Okay,
not done due to that. Maybe the some moisture issue or some particle size. So I have
did you
tried, sir.
extrude the filaments, or else did you extrude the
P,
filaments?
yeah, yeah, extruded filament. But
Mm.
if I reduce while reducing the wood fiber, then only it is possible. If I maximize the wood
Yes.
fiber, then the filament will not be
Mm.
extruded.
Yes, yes, definitely. And also, moringa powder will not have a good strength. Also, we have already tried
No,
with this kind of
Moringa wood fiber, sir. Moringa wood fiber.
that drumstick. Then you are telling at the drumstick powder,
No,
na?
no, drumstick is the croft. I am asking about the
Ah,
tree. Moringa tree.
tree.
Yeah,
Okay,
Moringa
okay,
tree wood
understood. Okay,
fiber.
okay.
Yeah, yeah.
How much the particle size you have maintained?
I have not measured, sir, but what should be the minimum size that is possible?
The thing is, you should be aware about the particle size. That is the thing.
Okay, sir. Okay.
If the size is good, na, the distribution was good. Pa. This is like a
Okay.
melting. It's similar to the extrusion head. Here, in the extruder also, there is a doing of melting only. Melting and
Okay.
mixing is happening inside the extruder. Okay.
Oh, yeah, yes.
So the particle size is minimal, and means it is easy to disperse evenly in the filament.
Yes, sir. So what is the minimum size, sir? What is the minimum size of particle?
Less than 50 micron, 50 micron, less than 50
Yeah, less
micron
than
should be
50 micron. Yeah, sir.
yes.
Okay. Thank you, sir. Thank you very much, sir.
Tomorrow session I will discuss more about this composite printing.
Yes, sir. Yes. Okay. Fine, sir. Fine.
Yeah, yeah.
Any other clarifications? I think no clarifications from participant side. Here I am sharing the feedback link. Feedback link. So once again, I thank Dr. Sabarinathan sir for spending his valuable time with us. Thank you, sir. We can wind up the session, sir. Thanks a
Thank you
lot.
so much.
Thank you.